Hello everyone, welcome to StudyMate again. From today on, we will start learning about this effects of forces. So let's start with resultant forces. So, what was the forces? Force was a push or pull that acts on an object due to interaction with another object. That is the definition. Forces can be after bodies in a variety of weights. For example, as you can see, the thrust of an engine can change car speed. So that means in change in speed, all that forces can cause bodies to speed up or slow down. So that's why we consider acceleration times mass is force. Also, change in direction, gravitational attraction. For example, forces can cause bodies to change the direction to travel, direction of travel with the force, using the force, or they can even change its shape. For example, can stretch it. So, for example, we have this rubber, we can stretch it or squash it. So this is also called force. So the resultant forces on a straight line. So the resultant force is a single force that describes all of the forces that are acting on an object. So when many forces are applied to one object or body, they can be combined or also called added to produce one final force that acts in the same way as the many forces. So, for example, we had many forces. We can combine all of them in a way that the force wouldn't change, but there would be only one force. So, a single resultant force determines direction of the force and also magnitude of the force. We need to calculate them separately, otherwise we could confuse. So, resultant force is called sometimes net force because it's all added force, combined force. Forces can combine to produce balanced forces or even unbalanced forces. Balanced forces mean that forces combine, when they combine it, they cancel each other and no resultant force acts on the body. For example, if I am putting force from this side and I am putting force from this side, and the resultant force is zero, as you can see, the object is not moving. So, this is also one more example, normal force and weight of the book, and the resultant force is balanced, zero. So now unbalanced forces. For example, two people in each side are pulling rope. This in the A side, that two people can, for example, exert 80 newton each, and overall it's 160 newton. And in the second part, maybe the most stronger man, and they could have 200 newton. So that overall net force would be we would subtract 160 from 200, and it's 40. So the net force or this resultant force is 40 newton to the B side. Its direction is also exact. So resultant forces can be calculated by adding or subtracting all of the forces acting on the object. For example, now we subtracted in that case. Forces working in opposite direction are subtracted each other. Forces working in the same direction are added together. So we, when it comes to two people acting from one side, we added 80 plus 80 and 100 plus 100, we said. So if the forces acting on the opposite direction are equal in size, when there will be no resultant force. So it is the same thing as I did this. When in both of my fingers, I'm exerting the same amount of force. So that's why force is cancelled out and resultant force is balanced. But in that case, as you can see here, both of the forces are acting on the same side. So direction would be to the left side, and resultant force would be 10 Newton. In that case, we would subtract it, 7 minus 3, 4, and bigger one on that side to the left. So now imagine forces on boxes as two people pushing on either side. In the first scenario, the people are evenly matched. Box doesn't move if they have same force. In the second scenario, two people are pushing the same side of the box. It moves to the right or to the left with combined strengths, depending on which sides these people are pushing. In the third scenario, two people would push each other in against, and the resultant force would be to the to the one with the bigger value. So, car travels along a horizontal road at constant speed. The image shows two of the three forces acting on the car. So this is the direction of motion, the force from engine, air resistance. So what we have to find? Calculate the size and direction of the third force. So now we'll get our calculator and 2000 minus 500, and it's 1500. Oh, sorry. 2000 minus 500, 1500. So as you can see here, the resultant force is to the left with 1500 this force at Newton. Worked example, calculate the magnitude and direction of the resultant force in the diagram below. So in the second side, let's add it in 12, and so we have 12 and 14. So we will subtract 12 from 14, and it's 2. As you can see here that we have one resultant force to the left with 2 Newton force. So now, let's move on to the Newton's first law. Newton's first law of motion. Newton's first law of motion states that objects will remain at rest, not moving, or move with the constant speed or velocity unless acted on by a resultant force. This means if the resultant force acting on an object is 0, the object will remain stationary if it was stationary before. If it wasn't and moving with the constant speed, it will keep its motion. And when the resultant force is not 0, the speed of an object can change. The direction of an object also can change. Applying Newton's first law. Newton's first law is used to explain things move with a constant or a uniform velocity. If the forces acting on this object is balanced, then the resultant force is 0, so that object can keep its constant or uniform motion, or the velocity can only change if the resultant force acts on an object is not balanced. A few examples with uniform velocity are shown below. So as you can see here, this a tablet stays at rest on a table because the contact force is equal to its weight. So that's why it keeps its stationary state. So comet moves through interstellar space in a straight line at a constant speed because there are no resultant forces acting on it. So it can keep its motion. Constant velocity can only be achieved when the forces of an object are balanced. In other words, when the resultant force is 0. So works example, Lima did some online research and found out that moon orbits the Earth at a constant speed of around 2000 meters per hour. She says that it's not an example of Newton's first law of motion. Lima is Lima correct? Explain your answer. So let's see what she says. Yes, moon has constant speed. So most of you may say that Lima is incorrect because if moon keeps its constant speed, then it's this Newton's first law of motion. But actually, in the first law of motion, as you can see here, it said if it's with constant velocity, and velocity is a vector quantity, so that's good if it has some constant speed. That is one of the qualities is ticked already, but it should have also constant direction. But as it moves around Earth, and Earth also moves around the Sun, it wouldn't have the same this exact direction. So its direction is always changing. That means that it is not Newton's first law of motion, and Lima is correct. Or you can explain it in another way, that this Earth has its this gravitational force, so that is acting on Moon. So now let's move on to the worked example 2. If there are no external forces acting on the car and it's moving at constant velocity, what is the value of frictional force? So if it's moving at constant velocity, that is the Newton's first law of motion. As most of you may guess that it is 0, but actually it's not. If it was 0, this driving force would lead to acceleration, because F equals m times a, that we will learn in the next lesson, Newton's second law of motion. Today it's frictional force. If it has no frictional force, it keeps getting accelerated, so its force would not be constant. Its speed would not be constant, even if its direction could be constant. That's why it wouldn't have constant velocity. That's why the overall resultant force needs to be 0 and balanced. So that's why frictional force should also be 3 kilonewtons. So goodbye everyone, and I will see you next time in the Study Mates physics class.